Hello, my name is Disha Vishwas, and today I'll be presenting my MSc research project, a decision support tool for optimized and resilient cybersecurity investment. So, without a further ado, let's get started. In today's world, cyber attacks are a daily threat for organizations of all sizes. But most decision makers are not cybersecurity experts, and they have to make important investment decisions with limited knowledge and tight budgets. My project addresses this challenge by making powerful optimization methods simple, transparent, and easy to use for non expert users. Here you can see the previous work. Like over the past years, researchers have developed complex mathematical models. Like in 2019, Kozani's paper introduced Tackleberg game theory and attack graphs. Then in 2021, Zhang and Malasari extended it with Bayesian's Tackleberg games. In 2022, tools like Cysic tools have shown that these models work well in theory, but they're often too technical or difficult for everyday users. And similarly, in 2025, again Zhang and Malaysia focused on resilience and uncertainty aware optimization. My work builds on these foundations, aiming to close the gap between academic research and practical, user friendly tools. Despite all these advances, there are still several barriers. Complex math models are hard for non expert users. Budget constraints make decisions tough. Many existing tools have outdated designs. Users lack clear guidance, and there is too much overwhelming data. My project directly tackles these issues by focusing on usability and transparency. The main question I set out to answer is how can we design a decision support tool that uses advanced optimization to help non experts choose cost effective, resilient cybersecurity controls with clear explanations? This project aims to make powerful security planning tools usable for everyone, build trust through transparency, and help organizations get better protection even with limited resources. My goal here is to develop a web based decision support tool that recommends the best cybersecurity investment using advanced mathematical optimization, but in a user friendly way. We formulate our model using techniques inspired by Stackelberg games, which lets us capture the interaction between defenders and attackers and design more robust investment strategies. Building a modern backend and frontend, ensuring explanations are clear, and testing the tool with realistic case studies. The backend is built with Python using Fast API and Perl for optimization. The frontend uses React with Material UI for smooth user experience and React Flow for visualizing attack graphs. MongoDB is used for efficient data storage, and all these technologies work together to create a responsive interactive application. Now, I'll walk you through how the tool actually works, from the home page to building scenarios and analyzing results. The home page welcomes users with clean interface. Here you can easily create a new scenario or find and manage your previous scenarios using search and pagination features. Everything is designed so users can start a risk assessment or optimization right away without needing technical skills. The dashboard gives an overview of your scenario's results. At the top, you see your security score and last saved info. On the left, there is an interactive attack graph where you can zoom and explore vulnerabilities. On the right, the playground. It lets you adjust parameters with tabs for optimizers, manual controls, path frontier, and explanation. You can also save your model or return to the builder at any time with all your data preserved. And then this scenario builder page. It guides users step by step. There are four main tables to fill: vertices, control groups, control levels, and edges. This makes it easier to define the network, available security control, and how everything connects. Built-in validation is there, which ensures that all required fields are completed correctly. So users can confidently move on to the dashboard for analysis. And the tool uses a mathematical optimization method behind the scenes. For every possible security control, the optimizer decides whether to include it or not. The goal is to pick the best combination that gives both the direct and indirect costs within budget, while reducing all the overall cyber risk as much as possible. We use a special kind of algorithm called a mixed integer linear program or MILP, which guarantees that the solution we get is both effective and efficient. To test the tool, we used a case study inspired by Kozani's paper. The scenario includes a small network with key assets and three possible security patches. Each control has its own cost and effectiveness. All data was loaded directly into the tool, showing how it can handle real-world examples. For this case, the optimizer selected three specific controls that reduces residual risk to almost zero, all while staying within the direct and indirect budget limits. The result here is clear, cost-effective investment recommendations that balance both protection and budget. The Pareto frontier. This graph visualizes how risk decreases as you invest more. The biggest drop in risk happens with the first few investments. After that, extra spendings has less impact. This helps users find the best balance between cost and security for their own needs. Here in the graph, you can see the elbow-shaped curve, which exactly defines that. The tool automatically creates an attack graph for every scenario. This graph shows all the possible paths an attacker might take and highlights where the biggest risks are. It's interactive, so users can explore the graph and see exactly how their choices will reduce risk. This makes complex information much clearer and easier to act on. The explanation tab. It gives a clear, itemized breakdown of why each control was selected. For each recommended control, you can see its cost, its impact on risk, and how much risk could remain if it was left out. This transparency helps build trust in the tool's recommendations and makes complex results easy to understand. In terms of performance, the tool is fast and scalable. It solves scenarios with up to 200 controls in under 40 milliseconds on my Apple M1 laptop, always using less than 1 GB of memory. Even as the problem size doubled, solve time stayed very low, meaning the tool is steady for real world use without lag or stability issues. Here I have just attached the table to show you the scenarios and their solving time, which clearly indicates the tool is very fast. For the next steps, we plan to make the tool even more practical and versatile. Advanced game theory features can be added so it handles smarter, more adaptive attacks and more complex situations. We aim to prepare it for larger real-world networks and expand the range of threats and defenses it can model. We'll also work on making the explanation even clearer so users always understand why a recommendation is made. Soon, the tool can be opened for the user trials to get valuable feedback from businesses and organizations. And finally, we are looking to enhance the resilience analysis so users can see how their security holds up against ongoing or sophisticated attacks. Finally, my key takeaways from this project are like I learned how to build a full stack optimization tool from scratch, balancing model complexity with real world usability. The main takeaway is that it's possible to bring advanced research into practical tools that anyone can use. I believe this platform has the potential to make a real impact by making cybersecurity investment decisions more transparent, accessible, and effective. And yeah, that's all. Here I have attached the key references that inform this whole project. And lastly, thank you very much for your attention and giving this wonderful opportunity to me. Thank you so much.